Okay, so we're going to look at the SIR model in Numerus Model Builder. The SIR model has three compartments: susceptible, infectious, and recovered. So this model, after you recover from infection, you move to this recovered class where you have immunity from infection, and we assume immunity lasts forever. So there are two flows between compartments in this model. We have an infection rate that takes us from the susceptible population to the infectious population. And as in previous models, we assume that rate happens that process happens at rate beta over n times s times I. And then we have a recovery process that takes people from the I compartment to the R compartment. And we assume that happens at rate gamma I. So there's a per capita recovery rate of gamma. And there are I infectives at any time, so the overall recovery rate is gamma times I. And then we can convert that all into a set of differential equations for the number of susceptibles, infecteds, and recovereds. So here we see the infection term, which comes in with a minus for the susceptible population because infection removes people from the susceptible group. It has a plus for the infected population because infection takes us into the infected group. And then we have the recovery terms, again with a minus for the infectious group because recovery removes individuals from the infectious group and moves them into the recovered group. And in this model, if you add up S and I and R, we get N, the population size, and that population size is constant, because in this flowchart we don't have any flows in or out from these three boxes, just flows between the three boxes. And because S plus I plus R is N, that means we only actually really need to track the numbers of susceptibles and infecteds, because once we know those two, we automatically know the number of recovereds because we just subtract S and I from N. We can also rewrite this model in terms of the fractions of individuals that are in the susceptible and infectious class. We can rewrite it in terms of X, which is S over N, and Y, which is I over N. And if you go through very little bit of algebra, you find that the rate of change of the susceptible fraction is just minus beta times X times Y. And the rate of change of the infectious fraction is beta times X times Y minus gamma times Y. Again, we only have to keep track of two of those fractions, because if the third fraction, the recovered fraction, X plus Y plus that fraction has to add up to 1, so we can always find that third fraction once we know the first two. Okay, so let's implement this model in Numerus Model Builder. So I'm going to call this model the SIR model. And I need to, so I have to think about, am I going to do this in terms of the numbers or the fractions of individuals? And let's do it in terms of the fractions. So we've got to be consistent. We either do it in terms of one or the other. And we've got to be consistent in terms of our variables. So if we're going to do it in terms of fractions, we need to set up our model in terms of X and Y. Numerus Model Builder would be confused and it wouldn't work if we set things up in terms of S and I and then set the equations up in terms of X and Y. So we either have to use S and I throughout or X and Y throughout. So we have X and Y, and we have a flow that goes from X to Y, and that flow is the infection process. And then we have a flow that goes from Y, I guess, to nothing, and that is the recovery process. Individuals leave that Y box. Got to make sure that flow is going in the right direction. Okay, so now let's click on this infection, and we need to set up the equation for this. So So this rate, the infection rate, is beta, let's just call beta b instead, times x times y. Notice little arrows have come from x to that rate and from y to that rate because Numerus Model Builder realizes that that rate depends on x and y. It's important that we put in the asterisks here for multiply, otherwise Numerus Model Builder gets confused. Also, if you have something with like a bracket in it, let me just write this in for a second. So imagine we just had alpha times, let's imagine we had alpha times y minus x. We need to put an asterisk there in between the constant and the brackets, because otherwise Numerus Model Builder, it turns out, thinks that we're talking here about a function called alpha that depends on the value of y minus x. But for us, we don't have this, so let's just delete that. The one thing we have to make sure is that that flow is going in the right direction, and we do that down here. The flow is in from x and out to y. So the flow is going from x to y, which is exactly right for the infection process. If we needed the flow to be in the other direction, we can choose different things here in these drop-down menus. And maybe you have to do it via choosing a blank, because it doesn't let you it wouldn't let me choose y here at the moment because y is already chosen on the other end of the arrow. So if I wanted to make the arrow go the other way, I think I'd have to choose it to be blank first, choose this one here to be x, and then choose this one here to be y. But actually I want the arrow going the other way, don't I? So let's do it again like that. The flow is out to y and in from x. Okay, now we've also now got the recovery to take care of. So we need to enter the recovery rate. And the recovery rate is gamma, and I'm going to call gamma g times y. And oops, again, I need to check the direction on this flow. Flow in from y, flow out to nothing. So again, it's going the right way. This arrow is coming in from y and going out to nothing. The terminology is a little bit unfortunate, I think, maybe. So there are a few other things I need to do. The first thing is I need to list all the parameters in the model. And so we have to have those as things on the diagram. So we had a b in this rate and a g in this rate. And one way to do that, well, when I have the rate here, I could hard code the value of b in here. So I could put it 0.5 or 2 or whatever here. Maybe a slightly better way to do it is to set it up as a variable. So here I've dragged out this thing called a term, and I can enter b for that name. And notice now an arrow goes from b to that flow because it knows, Numerus Model Builder knows that that rate depends on b. If I click on b, I can enter a value. So for example, 2. And I can do a similar thing here for the g, the gamma. Drag out another term, enter g in the name. Again, an arrow appears from g to recovery. If I click on g, I can put a value here, for example 1. What else do I need to do? I need to give the initial values to the states. So I can click on x, and down here I have init. So let's say I want to choose 99% of the population initially to be susceptible, so I put in 0.99. Similarly for infection, need to put in some infection initially, so let's say 1% of the population initially is infectious. And that is pretty much my model built. I could run this model, not quite. I need to tell Numerus Model Builder how to run this model, how to integrate this model. And so I need to tell it that this is a differential equation and what method to use to solve the differential equation numerically. And the way we're always going to do it is with this method here, RK4, Runge-Kutta 4. You notice Euler there, the forward Euler method that we've seen. We've said that's not a great method to use in practice, so this RK4 is a bit better. And then I need to set the time step for the numerical integration. So that's this dt, that's what we called h. So let's set this to something small but not too small, so say 0.01. The appropriate value there really depends on the problem. And so I could now save this model. Let's save as SIR model. Let's save it to my desktop. And I could run this model, and that would be great, except that I don't yet have a plot set up. So let's set up a display and control. And let's put in a line graph. So I'm going to drag out onto the screen. And I'm going to call that my plot. I need to go into the plot and tell it what I want to be plotted. So I come here and I can click on plus to add something to the plot. And I can go here to this drop-down box that says select, and it lets me plot the value of x, y, b, g, the infection rate or the recovery rate. So let's just put y on here. We'll plot the number, the infected fraction over time. You see there's an arrow here from y to the plot. So that's telling us that Numerus Model Builder knows that we're going to be plotting the value of y. Again, let's save our project. And now we're ready to go, I think. We click the launch button. Or maybe it's thinking about it. Okay, so here's my plot. And then I click the run button. And there's my output of the infected fraction over time for the SIR model. What do we see? We see infection spreading in the population, infection building up to a high level, and then dropping back down. Great, so we've done what we needed to do, what we wanted to do. Let's just improve a few things. Let's see, what might I want to do? Let's plot on my diagram both the infectious fraction, but also the susceptible fraction. So I can go back to my plot here, and I can click on plus. I can add another thing to my diagram. I can add x to my diagram. And it now plot those two quantities. Notice there's now an arrow from x to the plot. So let's do launch again. And I can run again. And there we go. So we see the outbreaks, we see the infection spreading, building up to a maximum, and then dropping away. And now actually this plot tells us why that infection spreads and then stops spreading, because we see as the outbreak spreads, the susceptible fraction drops. So the number of people around who can catch the infection is decreasing, and I guess eventually there are sufficiently few people around who are susceptible that there aren't enough people to sustain the outbreak, and so that's why the outbreak drops away. We've run this for one particular value of b and g. Let's see if we can do a bit better, and let's have a look at values for different, the output for different values of b and g. So let me replace these fixed parameter values here. So let me just do delete on that b, and actually maybe I'll leave the g as fixed. But I want to be able to change the value of b. So I'm going to come over here to the displays and controls and choose a slider. And I'm going to call that slider b. And if I click on that, I can choose the range of values that I want b to be able to take. So let's go have the slider going from 0 to 10 in steps of, let's say, 0.1. And let's have the initial value set to be 2. And something else I'd quite like is to have my plot automatically update as I do the slider, as I choose a new value. And apparently the way I do that is by choosing the continuous plot option on the plot. I believe that's how we do it. So let's save this. Actually, I'm going to save this with a new name. I'm going to save that with slider. And I'm going to launch this one. There we are. There's my plot. And you see my value of the slider here. So let's run this. There's the plot. Let's change the value of the slider. No, I know how it is. It's not continuous plot. I have to choose this auto. I think I have to choose that auto thing there. Let's see if that's what does it. Yes, it's the auto option there. And as I change the value of beta on the slider, the plot automatically replots. So we can see, for example, bigger values of beta give us like a bigger outbreak, a stronger depletion of the susceptible population. Smaller values of beta give us a smaller outbreak, plays out over longer time. We get a less severe depletion of the susceptible population. And if, we can't really see it on the scales here, if I choose a beta value that's less than my gamma value, that makes R0 less than 1, I actually don't get an outbreak. The number of infectives doesn't increase over time.